Welcome to Lecture 4 of General Chemistry. I hope you guys are keeping up with the previous 3 lectures and of course reading the material in your textbooks. Let's do a quick review before we actually go into today's lecture. So last lecture, Lecture 3, we looked at units of measurements. So once again, remember whenever you are reporting a unit of measurement, there are 2 aspects that are associated with that measurement, and that is a number followed by the unit. In other words, if you're asked what is the temperature outside, you do not just say it is 96, you say it is 96 degrees Fahrenheit, because that's the unit. We also mentioned that there are 2 systems that are used to measure quantities in chemistry and science, and one is the metric system and the other is the English system. We are very familiar with the English system because that is mostly used in the US. Whenever you go to buy gas, you buy a gallon of gas. So that's the English system. In chemistry, however, and science, and most of Europe, they use the metric system. So if we go to buy gas, we buy liters of gas because that's the unit of volume. As you can imagine, we will need conversion factors because conversion factors here will assist us in converting from one unit to another. So we often have to convert the unit of length, for example, inches and feet, into the metric system, which is typically centimeters and meters. So you'll need conversion factors for that, and last lecture we went over conversion factors. We also touched on temperature scales, and you'll notice here that there are 3 temperature scales that are typically used. We're more familiar here with the Fahrenheit scale. But another one that's typically used is the Celsius scale, degrees C. That's mostly used in Europe. And of course, another one that's used in science mostly is the Kelvin scale. Okay? And there are conversion factors to convert from the Fahrenheit to Celsius or vice versa. And we can convert from the Celsius to Kelvin. So again, look out for these conversion factors and be able to use them. Lastly, we looked at the states of matter. We mentioned that there are 3 states that matter can exist in, and those are the gas, the liquid, and the solid. So once again, you should be able to define these states. And if given a state of matter, you should be able to tell if it's in the gaseous state, the liquid state, or the solid state. So if I were to ask you, there is some water in the freezer, it's been there overnight, and the temperature of the freezer is below 0. What state is that water? Of course, as you know, that would be ice. So ice is a solid state of water. Okay, so let's look at today's lecture. So what we'll do today is we'll look at another property that's called density. This property is a physical property. Remember that physical properties are properties that are measurable and observable. Observable, such as water is colorless, that's a physical property. Water has a boiling point of 100 degrees C, That's measurable. So that's a measurable physical property. Another property of molecules or of compounds of matter is its density. And density here is defined as the ratio of the mass to volume. Ratio. So here's the equation. Density is equal to mass over volume. We know the unit of mass here in the metric system would be grams, and we know the unit of volume in the metric system would be milliliters. So let us apply this concept here, or this definition, to determining the density of a substance. And the example is given here. If 73.2 milliliters, notice milliliters here, that's a unit of volume, of a liquid has a mass of 61.5 grams. That's a unit of mass. So here we have the mass and the volume. So all we need is to calculate the density. So here's the equation. So the density is now equal to 61.5 grams, the mass, divided by 73.2 milliliters, the volume. You plug these numbers into your calculator and divide them through, and you get as an answer 0.84 grams per milliliter. Notice the unit of density here. You always have to put the unit whenever you have a measurement to report. Okay, let us look here at an application. Of course, as you know, one of my emphasis here is to have you guys not only know the definition of terms that we use in chemistry, but be able to apply these concepts to solving problems. So here is one. And let's read this through and then we'll solve it. So aluminum has a density of 27.0 grams per cm cube, cubic centimeters. That is the same as milliliters. That's synonymous with milliliters. What volume is occupied by a block of aluminum which weighs, notice that's the mass, 4.3 kilograms. So let's see what we have and what's being asked. We have the density. We need to find the volume that's been asked. We have the mass, which is 4.32 kilograms. So we can use this conversion factor here, or that equation, to determine the volume. So here you'll have to resort to some of the math that you did back in high school or back in your algebra class to solve an unknown in an equation. Notice again, that's what's given is the unit here is in kilograms. And we know the unit for density is grams over milliliters or cubic centimeters. So we'll have to convert this 4.3 kilograms to grams. Here is the conversion factor. 1 gram is equal to 1 times 10 to the third grams. Here again is your scientific notation. So again, make sure you have a calculator that you can use your scientific calculation, your scientific notation. So let's convert first this kilogram here to grams using the conversion factor. Here's the conversion factor right here. And it's set up so that kilograms will cancel kilograms, leaving grams as the answer. So this is 4.32 times 10 to the third grams. Now we have the weight. This is the weight in grams. So all we need next is to substitute that into that equation here. Making that substitution, 2.7 grams per cubic centimeter or liters is equal to 4.32 times 10 to the third grams, and that is now divided by the volume, which is our unknown. So using the algebra, we can solve for this unknown here, volume, and it works out to be 0.63 cubic centimeters. Look at the units carefully. We could also use milliliters here, ml. But the bottom line is this number here is of importance for the volume of that aluminum. So what you should be able to do is to utilize this equation here to calculate any one of these unknowns, the density or the mass or the volume, of course, if given the others as known. The next slide gives you an example of you utilizing that knowledge. Okay, so let's apply what you've learned here. So in this case, let's look at this problem. And this is a typical question that you will get on your quiz or on your exam. So titanium has a density. So density is given 4.54 grams per milliliters. That's the density. What is the mass or the weight? So this is the unknown here, the mass. If 17.3 milliliters, that now becomes the volume. So this is given. I will always give you the conversion factor. Okay, I will always give you what to use in your calculations. So let's see. We have here the density, and we have here the volume, and all that's needed here is the unknown. We're asking here to calculate the unknown. So what you need to do is to get your calculator, get a piece of paper, and set up this equation and plug in these known values and determine what is the mass. So you may want to pause the video at this point and do that calculation and determine the best answer here. The next slide has the answer. So after you've done the calculations, what you will see here is that as the answer. Notice that it's reported to 1 decimal place. Why? Because the least precise number in that calculation is reported to 1 decimal place. Even though the density is given to 2 decimal places, the least precise measurement that was obtained from the experiment is to 1 decimal place. This type experiment is very important because it can be used to determine the mass or the volume of different unknown, or it can be used to determine the density of different unknown if given the volume and the mass. Let us look at a practical application of this concept. So if I were to say to you, we have here a separatory funnel. And if you're taking the lab, you will see this type equipment in your lab. It's called a separatory funnel. It has 2 liquids in it, water, and it also has carbon tetrachloride. Carbon tetrachloride here is an organic solvent. They are immiscible. In other words, carbon tetrachloride will not mix in water to give a nice solution. You will have 2 layers, or you will see 2 layers. 1 layer on top and 1 layer at the bottom. If I were to tell you that carbon tetrachloride is more dense, the density of carbon tetrachloride is greater than the density of water. What is the layer that would be on top? As you can see here, since water is less dense than carbon tetrachloride, it would be at the top. And since carbon tetrachloride is more dense, or the density is greater than that of water, it will be at the bottom. Let's apply that down here. So if I were to tell you that we have a mixture of water and diethyl ether. Diethyl ether is again another organic solvent. So if I were to tell you that diethyl ether and water, they do not mix, they are immiscible, they will form two layers. In this case, diethyl ether is on top and water is at the bottom. If I were to ask you, out of water and diethyl ether, which is more dense? Which has a density that is greater? Again, the concept here is that the more dense liquid will be at the bottom. So in this case, water is more dense than diethyl ether. This is true again if you should mix water and oil. Oil will go to the top, which implies that oil is less dense than water. Okay, let's look at another property here, and this property is called specific gravity. So this is another physical property of matter. It's measurable. You can go in the lab and measure the specific gravity. However, let's look at the definition first. The definition is the density of a substance compared, notice keyword here is compared to water. So it's a ratio, it's a comparison. It's a comparison. You notice here that it's dimensionless or unitless. Why? Because it's a comparison and the units are the same because they are comparing here densities. So let's look at an example. The density of copper is 8.92, and since it's density, the unit is gram per milliliter. The density of water is 1, and the unit here is gram per milliliter. So once you set up that ratio here, the units will cancel, giving just a number. So specific gravity is just a number. In this case, an exception is just a number for a specific substance. Copper, for example, it's 8.92. That's the specific gravity of copper. Let's see an application of this concept. So here we have an instrument we call the hydrometer. Here it is right here, which measures the specific gravity. So if you take this instrument and you put it in normal urine here, it registers here a specific gravity for this liquid of 1.03. On the other hand, if it's not normal urine, as over here, it will show a different specific gravity, which is not 1.03. In this case, it shows 1.06 as a specific gravity for this liquid over here, which means that it's not normal urine. So especially for the individuals who are in the medical profession, this is one way that we can determine if urine is normal or not. One thing I should point out again here is the precision of these numbers. 1.03 and 1.06. Okay, they're different numbers because the instrument that's used to measure the specific gravity of these instruments is precise enough or expensive enough or has enough markings here that you can get 2 decimal places. And that's the only way you can tell that these two numbers are different, because the instrument is precise enough to tell you that these numbers are actually different. Okay, let's look at another concept here, and that is the concept of energy. So as usual, let us define energy, and then we will give you some examples, and then we'll apply that concept. So first, energy is the capacity to do work. Capacity to do work. Okay, so think about that for a second. Capacity to do work. So we'll have to define work and the capacity in a second. There are 2 forms of energy. The first is kinetic energy, KE. Let's define that. Energy in motion. So it's now energy that's in motion. Work in motion. Okay? Examples. Water flowing down a waterfall. Flowing in motion. Mechanical energy. So if you turn on a pump or you start your car, it's in motion. It's spinning so that the car can move. Light, that's energy in motion because the photons are constantly coming at you or at an object so we can see. Heat, the heat waves are constantly going out to keep things warm, in motion. Electrical energy, energy in motion. Electrons are constantly circulating to give you that energy in motion again. So from this, what you should be able to do is to take any example and utilize this definition here, energy in motion. Key here is in motion, to determine if it's kinetic energy or not. Let's look at this example here. As you can see, here is a dam and the water is coming down. Water in motion. Therefore, this description here is kinetic energy. Let us look at the other form of energy. This is potential energy. Let's look at the definition. This is stored energy. Stored. That means it's not in motion, but it is stored. It can be in motion. And if it does go in motion, it becomes kinetic energy. But at one state, it is stored. Let's look at some examples. Water at the top of a waterfall. The top. It's not moving. It's just sitting there at the top. But it has the potential to go down to the bottom of the waterfall, which means that it can be converted into kinetic energy. Chemical energy stored in a substance. Okay, so when we start doing reactions, we'll see that a lot of the energy are in the bonds of these molecules. And once the reaction occurs, then the energy is released. But before the reaction occurs, the energy is stored in the molecules. Food, such as carbohydrates and fats. Of course, as you know, we ingest these foods so that we can get energy. But before you ingest it, it is energy that is stored. Energy that is stored. Once you ingest it and it starts to oxidize or break down, it produces energy. nuclear energy. We have a chapter on this later on in the course, but in the atoms itself, there's energy in the atom, and it's stored. But once you open that up in terms of a nuclear bomb or something like that, nuclear energy is released. So you should be able to look at any description or an example and determine if it's potential energy or not. Let's look here at this example. So this is a dam. As you can see, it's protected here by this wall, and a lot of water on top here, but it is not moving. The energy is stored. Once you open the valve of the dam down here though, and it starts coming out, then that's energy in motion, kinetic energy. Of course, as you know, that's how you get the hydro energy, by turning a turbine, because the water is moving. That's energy in motion. So you should be able to look at any example of energy and determine if it is kinetic energy or potential energy. Okay, let's look at here another concept, and that is the calorie, which is the unit of energy. So now what we'll do is, for the next few slides, what we'll do is we will determine quantities of energy. How much energy is used in accomplishing a particular job or task or work. And the basic unit here is calorie. Okay, so we'll define that in a second. But let's just cover a law here, which is the conservation of energy. Energy can neither be created or destroyed. So as you see, you have potential energy, which is the water sitting at the top of a dam. And when you open the valve, it comes down. So that's kinetic energy. So it's just transferred. It cannot be created or destroyed. Energy can be converted from one form to another. As I said, if you open the valve of your dam, the potential energy, which is stored in the water at the top of the dam, is now converted to kinetic energy. That law, notice again, the law that we discussed earlier as part of the scientific method, it's been around for years. It's been proven by lots of experiments. So it becomes a law in science. So the law of conservation of energy has two aspects, and here they are. Let's look at another concept before we start doing our calculations. Heat, of course, as you know, is a form of energy. Heat is a form of energy. Temperature, however, as a definition, is a quantitative measure, or using numbers to measure how hot or how cold is a substance. So it's not energy. Temperature is not energy. It is a measurement of how hot or how cold something is. Heat is the form of energy. Here's a classic example. If you have here 100 mils of water at 80 degrees C, that's pretty warm, but it's a small quantity. And you compare that now to 1 liter, which is 1,000 mils of water at the same temperature. Notice the same temperature. I am sure you will agree that this water here at 1 liter of this water will cause a greater damage in terms of burn compared to 100 milliliters. So again, there's more heat involved in this 1 liter of water at 80 degrees compared to 100 milliliters of water at the same temperature. Less heat. So we have less heat over here and more heat here. So that's the difference between heat and temperature. Okay, let's look here at some applications. Heating refers to energy transfer when two objects of different temperatures are brought into contact. So if you have something that's really, really hot and something that's really, really cold, and you put them together, have them touching each other, over time the heat from the hot object will be transferred to the colder object. As you can imagine, there will be a temperature difference once this heat has been transferred. So I want you guys to probably pause the video here and think about that. A hot object mixing with a cold object. Given time, the heat from the hot object will be transferred to the cold object, and there will be a temperature difference. Okay, let's look at some aspects here. So heat always flows from the hotter object to the cooler object. That's just what I've just described. So the hot object, if mixed in a cold object, the heat from the hot will go to the cold until it gets to the same temperature. Until it gets to the same temperature. Okay, heat is commonly measured in calories. So again, here will be our units. So how do we tell how much heat has been used up? We can tell based on the unit of calories. How do we define calorie? Calorie is, let's go here to the definition. A calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Notice the unit, 1 degree Celsius. So if you get 1 gram of water and you apply heat to it and the temperature goes up by 1 degree Celsius, you have applied 1 calorie of heat. Okay, let's go back to this one. The unit that we'll use here is a calorie, but you will see, or you may see, another unit which is called the joule, and there's a conversion factor. So if we happen to give you heat in the form of joule, we'll give you that conversion factor. But for this course, we will stick to the unit calories. Okay, so let me see if we understand what we just described here. So here's a question. A typical question that you probably will get on the quiz or on the test is a multiple choice question, of course. Which of the following statement is true? I'm underlining is true because I want to make sure that I understand my question before I start answering. So let's look at these. Both heat and temperature are forms of energy. That may be a little problematic here because we know that temperature is just a measure of how hot or how cold. Neither heat nor temperature is a form of energy. Another problem here because we know that heat is a form of energy from definition. Heat is a form of energy, but temperature is not. That sounds like it could be reasonable, but let's go on to the last choice. Temperature is a form of energy, but heat is not. So again, I'm doing this deliberately, step-by-step analysis, because that's part of the training of a scientist. Again, when these questions are asked, you do not know the answer, but your job is to utilize the concepts that we have discussed and apply them to solving a problem. That's exactly what we as scientists do, is we solve problems. So you may want to pause your video at this point and think this through again, because the answer is on the next slide. Think it through again, analyze it, visualize this as you think through what's possible here, and then come up with an answer. Let's see what the answer is. So the answer is no surprise, this one. Because the definition, heat is a form of energy and temperature is not a form of energy. It's just a measurement of how hot or how cold a substance is. So again, guys, remember, your job is not to memorize this material, but your job is to understand the concept. And your job is to utilize that understanding to solve problems. Let's look at another concept here in chemistry, and this is the specific heat. Again, this is a measurable property of a substance. We'll define the specific heat as the amount of heat, we know what heat means now, necessary to raise the temperature of 1 gram. Notice 1 gram of a substance by 1 degree Celsius. Think that through again. Heat, unit of calories, the amount of calories necessary to raise the temperature of 1 gram of substance by 1 degree C. So you can imagine if you had water, 1 gram of water, the amount of heat required to raise the temperature of 1 gram of water by 1 degree C is the specific heat of water. And that is a measurable quantity. It turns out to be 1. So that is a property, a physical property of water. So the specific heat of water is 1, notice the unit, calories per gram per C. Calories per gram per C, because that's how it's defined. Here's some examples here, so you can see copper has a specific heat here of 0.092, and aluminum has a specific heat of 0.22. So you can determine from this which is better at transferring heat. So let's think that through for a second. We'll work problems like that in a second. If you went to the hardware store and you wanted to buy a pot that you can use to heat your cooking, which is a better pot to buy? An iron pot, an aluminum pot, or a copper pot? So again, we'll get to that in a second, but I want you guys to think about that as we go through this course. Okay, let us concentrate now on utilizing this concept. So, the following equation gives the relationship between specific heat, the amount of heat, and the mass that's required for a change in temperature. So once again, as I mentioned earlier, if you have a hot object and you mix that with a cold object, at some point the temperature will be changed from that hot object to a colder substance. And of course, the amount of heat that's involved can be calculated. Here is the equation. The amount of heat is equal to the specific heat, which we just looked at. And remember, that's a physical property, so it's a constant for every substance, times the mass of that substance. So you'll have to know the mass of that substance. How much of that substance did you mix with that cold substance? And of course, the change in temperature. So it's going to change from a temperature where it's hot to a temperature where it's much cooler because of that heat that's lost. So another way of writing that equation is shown right here. Notice this is T2 minus T1, or the T final minus T initial. The temperature at which it ends up with minus the temperature at which you started with. So your job will be to utilize this equation, this concept, to calculate the amount of heat given different situations. Here's an example. How many calories? How many calories? So that's heat. So it looks like we're going to calculate heat. Are required to heat, yes, 352 grams of water. So that's the weight. So here's the weight. From 23 to 95. So this represents here the change in temperature. The specific heat of water, which is a constant, is 1. So it is right here, and that would be what's substituted here. So all you have to do is to take this equation here and substitute these numbers into it. So here we go. The amount of heat is equal to the specific heat, which is 1 calorie per gram per cc. And again, I'm encouraging you to write out your units, because you will see that they do cancel and it gives you the appropriate unit for your answer. Times the mass, and here's the mass, 352 grams. We know it's the mass because of the unit. Here's where it becomes a little tricky. Times the change in temperature. So we started out at 95 minus 23. So here's where you have to use your calculator. What I would suggest is to do this calculation first. So 93 minus 22. And then multiply that by 352 and multiply that by 1. Your units will cancel, and what's left here is just the calories as shown here. So this should be your answer. This should be your answer here, which is 25 times 10 to the 4th calories, a large number. Or if you want, you can report that in kilocalories. Remember, the conversion here is 10 to the 3rd. So a calorie is equal to 10 to the minus 3rd kilocalories. Okay, so let's look at this. Here is an example. So here's a question that you may get, or something that you may get like it. You won't get this exact question, but something very close to it. So let's read this through, take our time to read it through to make sure we understand it, and then we do the calculation. The specific heat of copper is this. So this is a constant. That is the property of copper. Specific heat. Notice the units here. Oops, I should have included that as part of the number. How much heat? So what we're asking here is heat. How much heat is required to heat 40 grams? So that's the mass. From 25 degrees C to 75. So that's the change in temperature. So let's see. Here is the equation. And again, I'll always give you the conversion factor or the equation. You just have to substitute the numbers into the equation. So you'd have to go back to your question and identify these numbers and substitute it into the equation. So once again, get your paper, get your calculator, write this equation down, and substitute these numbers into this equation and do your calculation. So you may want to pause the video here and do the calculation and see which one of these answers here corresponds to, or the best answer for that question. Here's what I have. This is the best answer here, 184 calories. So that's the amount of heat required to change the temperature of 40 grams of copper from 25 degrees C to 75 degrees C using this equation. So once again, you won't see this exact problem, but we can change this from copper to iron. Of course, this value here would be different. And of course, you can tell from that how much heat is required. So now you can see, if you went to your hardware store, would you prefer to buy a copper pot or an iron pot based on how much heat is transferred into just heating up the pot as opposed to heating up your food. Let's see what's on the next slide here. Here's another example. This one here is a little different because we are using we are required to calculate something different. So let's read it. It required 82 calories to heat. So this is a unit of heat, which is right here. To heat 14 grams, which is the mass of an unknown substance from 24 to 175. So that represents here the temperature change. So it's asking you, what is this specific heat? So again, think it through carefully. Think it through carefully and analyze what's being asked. So get your calculator and get a sheet of paper and write down this equation here and substitute these numbers here into this equation. You will see that the only unknown is this specific heat in that equation. So you'll have to use your algebra again to solve for that unknown. Notice T2 minus T1 is the difference between 175 degrees C and 24 degrees C. Make sure you can do that calculation. I can tell you from now, you will see it on the quiz and on the test. So again, the answer is on the next slide. So go ahead and do the calculation and see what you get. Okay, here's what I got. I got this as my answer C. Notice the units because it's asking for specific heat, and I know the unit for specific heat is calorie per gram per degree C. Per degree C. So this is the specific heat of this unknown substance. I should point out here, because the specific heat is a physical property that's unique to a specific substance, oftentimes in chemistry we can determine what is an unknown substance by calculating the specific heat. So once you determine the specific heat or measure the specific heat based on going in the lab, you can determine the what is an unknown compound. Okay, so once again, make sure you can use this equation here to solve just about any of these aspects: the heat, the specific heat, the mass, or the change in temperature. We probably won't go there because it's a little more complex to do that calculation, but just the heat, the specific heat, and the mass. That's the end of chapter 1. So we are finished with chapter 1, and so I again go back and make sure you understand all the concepts here in chapter 1, make sure in addition you can apply them to solving questions, solving problems. Make sure you think through these problems and visualize it sometimes and apply a concept that can be used to solve these problems. Okay, so I will post lecture 5 shortly, or the next lecture shortly, which will be on chapter 2. We'll start chapter 2, so look out for that one. Okay, continue studying hard. Okay.